Let's look at one last form of modulation, digital modulation. We're going to take, again, the message signal. Let's take polar, non-return to 0. So we have logical 1 is 1 volt, logical 0 is minus 1 volt. And we'll take that into a voltage-controlled oscillator so that this controlled voltage changes the frequency of oscillation for this oscillator, and that produces a frequency shift keyed for signal. The message signal equal to +1. The frequency shift keyed signal as a function of time is going to be cosine, and we have a 2 pi, and here we have FC plus delta FM. Sorry, delta F times T. Let's see. I don't need this part in the equation. It's just 2 pi FC plus or minus delta F times T, or I could have it just plus delta F times M of T. I don't need it both ways. And then for the message signal equal to -1, the frequency keyed signal is going to be cosine 2 pi FC minus delta F times T. If we look at the spectrum for of the modulated the frequency modulated signal, for if we kept the message signal equal to 1, what we would have is this is plus and minus the carrier frequency. We would have the modulated signal would be at the carrier frequency plus delta F, so it would be a delta function. This would be at FC plus delta F, and this is at minus FC plus delta F. So if we kept the message signal equal to 1, the frequency of this voltage controlled oscillator would simply be at FC plus delta F, and for the message signal equal to -1, in like fashion, here is FC and minus FC. The delta function would be here at FC minus delta F, and this would be at minus FC minus delta F. Okay, so delta F is the frequency deviation, just as we spoke about with frequency modulated signals, and depending upon the message signal, the value of the message signal, we are either transmitting the modulated carrier is either at FC plus the frequency deviation, or it's at FC minus the frequency deviation. Now when the message signal is a random binary signal that is changing rapidly, that will spread the spectrum of the frequency modulated signal beyond these 2 points, and we'll see that in the numerical analysis, or the numerical simulation. So here's the polar non-return to 0 signal. Logical 1 is 1 volt. Logical 0 is -1 volt. It's a random string of 1s and 0s with a certain bit period. The carrier signal has a nominal frequency of the carrier frequency, and then the output from the voltage controlled oscillator is depending upon whether the message signal is a +1 or -1, will either have a frequency of FC plus delta F or FC minus delta F. So this is clearly a frequency modulated signal. Now if we look at the spectrum, I had MATLAB take the Fourier transform of these signals to estimate the spectrum. And for the carrier signal, we get a pair of delta functions at plus and minus FC. For the baseband digital polar non-return to zero signal, we get that sync squared shape with the first null happening at the bit rate, and took the Fourier transform of the frequency shift keyed signal, the frequency modulated signal, and this is what MATLAB shows as the spectrum of that signal. And you can see we have this is the carrier frequency, and we've got a strong line, a delta function at FC plus delta F, and we've got a strong line at FC minus delta F. But as the signal changes back and forth rapidly between these two frequencies, we get this spread in the spectrum, just as we do with an FM signal. And you'll notice it's as if we took this sync squared shape and replicated it at FC plus delta F, and you take the same sync squared shape and you replicate it at FC minus delta F. And now when you look for the overall bandwidth of this frequency modulated signal, we've got, see, this is the carrier frequency, this is FC plus delta F, and then we go beyond that to this point, which is going to be, this is going to be at FC plus delta F plus the bit rate, because this is the bit rate gives us the bandwidth to the first null of this sync shape. So this is FC plus delta F plus the bit rate gives us to this point. This point on the other side is going to be FC minus delta F minus the bit rate. That gives us this point. And the overall bandwidth is the difference between the two. So that's going to be, we take FC plus delta F plus the bit rate, and we subtract FC minus delta F minus the bit rate. When we do this, FC minus FC is 0. Delta F minus a negative delta F, that's going to be 2 delta F, and then bit rate minus a negative bit rate, so plus 2 times the bit rate. So that gives us the overall bandwidth of 2 times delta F plus the bit rate. Okay, so, and this is exactly Carson's rule again. We have twice the frequency, we take the frequency deviation plus the bandwidth of the message signal and add them together, take twice that. By Carson's rule, that gives us the bandwidth, and we see that same rule applying to this digital signal as well. Okay, to demodulate the frequency shift keyed signal, if we take the frequency shift keyed signal and then just as we did with FM, we need to put it through a frequency discriminator. Not sure if that's how you spell discriminator or not. So that the signal that comes out is both frequency modulated and amplitude modulated. Then we can take this signal and through a peak detector. And a low pass filter. Then perhaps a comparator, and we get out the binary signal again. To see graphically what this might look like, if we take this set of equations for the frequency shift keyed signal, and for the frequency discriminator we'll take a differentiating amplifier, so that we have for m of t equal to 1, we've got phi, the frequency shift keyed signal, equal to cosine 2 pi fc plus delta f times t. We then take this signal into a differentiating amplifier to do the frequency discrimination, just as we talked about with the AM signal. And what we get, let's see, we've got the derivative of cosine, and I think the derivative of cosine is minus the sine, if I'm not mistaken. So this is going to give us minus 2 pi fc plus delta f times the cosine of 2 pi fc plus delta f times t. So this would be the signal that results from the frequency discriminator when the message signal is 1. When the message signal is minus 1, and the frequency shift keyed signal is cosine 2 pi fc minus delta f times t. We take this through the differentiating amplifier, and the signal that comes out is going to be a minus 2 pi fc minus delta f times the cosine of 2 pi fc minus delta f times t. The inversion is not of any significance to us. What is of significance is the fact that the higher frequency cosine has a larger amplitude than the lower frequency cosine, because we have fc plus delta f here, and this is fc minus delta f. So that would result in a signal that would have would take this shape. I'll just draw a small sample of it here. So when the frequency is higher, the amplitude is larger, and when the frequency is lower, the amplitude is smaller. Okay. So taking the frequency shift keyed signal through this frequency discriminator, as illustrated by this differentiating amplifier, will produce a signal that's both frequency modulated and amplitude modulated. Then this can be passed through a peak detector. This would be a rectifier. Then the low pass filter, and what would result is a signal for logical 1, and then 0 and 1, and then all that would take is some form of a comparator to turn this back into a proper digital signal, and we've demodulated the FSK signal.